Okay, so we're going to run a linear regression in SPSS, following on from our last video that calculated this manually in Excel. And here we're using the same data set, so we have our 5 repetition max and our 1 repetition max. And we want to be able to see whether we can predict someone's 1 repetition max using 5 repetition max as a predictor variable. So I've got the data here into SPSS, and it's just a standard long format, a 5RM, and I've listed this clearly as the predictor. 1 repetition max is the outcome. In variable view, make sure that you have these selected as scale or high level data. Our first assumption is that we have a linear relationship between our two sets of data. So if we go to graphs and to chart builder, we want to select a scatter plot here, and we can drag this up into the bigger box, which will select it as a scatter plot. Remember that to plot any data on a scatter plot, we have to make sure that the predictor variable is always on the x-axis. So in our case, we want to use 5 repetition max to predict 1 repetition max. So 5RM in this case goes on the x-axis, and 1 repetition max just dragged across onto the y-axis here. We're going to click OK, and this should generate a plot that we see like this. And what we see is a very clear linear relationship in our data. One thing that I've added in deliberately is one deliberate outlier, as you can see up here. So with the exception of this outlier, we have a very clear linear relationship in our data. It's a positive linear relationship, and it appears to be quite strong given the linearity that we see. Again, I've put this in here, this outlier, because I want you to be able to see on the output of the linear regression statistic how we would identify this. So it's here for an important reason. We're going to leave it here for now. Remember that a second assumption with our primary data is that we do have no outliers. So ideally we would remove this beforehand. And I'm going to leave it here just for the purpose of this demonstration. So to run our linear regression, we go to Analyze, Regression, Linear. In our box here, we put our dependent variable is in our case our outcome variable, our 1 repetition max. Always consider that the independent is the one that we're going to attempt to use as a predictor for the outcome variable. In our case, it's a 5 repetition max. So in other words, the 1 repetition max will depend on the value from the 5 repetition max. We're going to click on Statistics, make sure that we click Confidence Intervals, Model Fit, and Descriptives. Make sure we've selected Durbin-Watson and Case-Wise Diagnostics, and this is what we use to attempt to establish any outliers in our residual data. And we want to make sure this is set at 3 standard deviations, which is the normal for SPSS. In our plots, we need to plot our 2 residuals to see whether we have homoscedasticity. So our y-axis will be the z residuals, which is this one here. So we put z residuals on the y-axis and z PRE on the x-axis. Also select histogram and normal probability plot, because if you recall, a further assumption is that we have a normal distribution in our residuals. So we're going to click Continue here. Again, always check your other options. One thing that we want to select in the Save option is our standard error, or our standard error of the estimate, or SEE statistic. We've calculated this manually in Excel, but we want SPSS to do this for us. Let's go ahead and click OK. It should bring up our data here. So again, as usual, the first thing that we do is ignore the actual statistical outcomes. We first have to resolve all of our assumptions. We've established that we have a linear relationship with the exception of one outlier. So let's first check for outliers of the residuals. And you'll find that under case-wise diagnostics, as you can see here. Case-wise diagnostics is what we selected to determine whether our residuals were above +3 or below -3 standardized residuals from the mean. We can see here that case number 23 is indeed outside of this acceptable range. So that means we have to go out then and delete number 23 as one of the outliers in our residuals. And of course we check this first because we need to delete this outlier before we proceed with the analysis. So let's close down this window, delete case number 23, which you recall I put in deliberately, and then rerun that second statistic again. And most of the options will be saved in SPSS if you've left it open. So we'll just go to Analyze, to Regression, Linear, and click OK again, and all of the other options will be saved for us. Now when we come back into our regression output, we'll see that there is no case-wise diagnostics output here. And that's because we have, therefore, no outliers in our regression formula, or in our residuals. We then need to establish whether we have an approximate normal distribution of our residuals. So when we examine the test of the normality or the distribution of the residuals, we can use this outcome here, and we can see a box plot with our bell curve overlaid. Now if we wanted to, we could go and actually establish the residual as a separate statistic and go and run our normality test as we would with our standardized protocols, but we're not going to do it in this case. We're going to assume or look at this and say, well, we have an approximately normal distribution. Most of the data is centered higher in the middle here, and it tends to plateau off as we move to the extremes. There is an exception here, of course, you can see, but we'll never have a normal or exactly perfect distribution in our data. We also need to look at our PP plot to determine whether we have any skewness in the data. So each of our data points should approximately lie along this line, and we can see that most of them are. There's no major deviations of a whole load of data moving away from this point. So we do have an approximate normal distribution. Our final assumption is homoscedasticity. And remember, when we plot our residuals onto a scatter plot like this, there should be no uniformity or any pattern taking place for us to have passed this test. In this case, we can see that the dots are pretty much randomly distributed all the way across the page. This is a very difficult one to establish using an objective mean, to really just look at the graph and determine for ourselves whether there's any pattern or not. In this case, there is no patterns taking place, so we can say that we've passed this test. So we can then proceed to evaluate the outcome of our linear regression analysis. When we look at the correlations, we can see that we have indeed a high correlation between 1 repetition max and 5 repetition max. The R value of 0.98 is exceptionally high. And as you can imagine, if we then extrapolate this to our R squared, which is in the model summary, our adjusted R squared is 0.96, or 96% of the variance can be explained by 5 repetition max, which is a very strong model. This is suggesting that we can indeed very accurately predict 1 repetition max from 5 repetition max. The model is significant, a significance here of p equals 0.000, and the same, of course, as you recall, for the regression and the ANOVA, since they're the same thing, will give us an identical p-value in this case. So our model is significant, and therefore we reject the null and accept the model that we have a significant predictor here for 1 repetition max. In the model summary, we also have our standard error of the estimate, which says that the typical error that we would see in predicting 1 repetition max is somewhere around 3.3 kgs, or 3.36. Now you might recall, if we compare this to our Excel that we did last week, we actually manually calculated standard error of the estimate. We can see here that our outcome was 3.37 kgs, and this is rounded up. So if I take my standard error in SPSS and round this up, we arrive at 3.37 kgs, so identical to the one that we have manually established. The final thing that we need to do is establish our regression formula, and for this we go to the coefficients output, and here we have what's called our unstandardized coefficients. Our constant, which is our intercept, which is at 6.49, and our predictor, which is the 5 repetition max at 1.037. Now we can use this to establish how much of one influences the other, and this tells us, the 1.037, that for every increase in the 5 repetition max of 1 kg, there is an increase in the 1 repetition max of 1.037 kgs. So for every 1 unit that the predictor goes up, this is the change that we multiply the outcome variable by. Now again, these may be familiar because, again, if we look at our Excel output on our scatter plot, if we look at our regression formula, we can see that y is equal to 1.0373, which is this predictor B coefficient here, plus 6.497. which is again this one just rounded up, 6.498. So these two establish or become our regression equation, and that's why they're important. Now, as well as that, importantly, we should report the 95% confidence interval for this predictor coefficient for the 1.037. Now remember that this assumes that there's an exact value, but we know that this isn't true. So instead, we can then report, well, for every 1 kg increase in the 5 repetition max, there is somewhere between a 0.94 and a 1.13 kg increase in the 1 repetition max. So we have a range of possible values, which is of course the value of our 95% confidence intervals. So there are all the statistics that you need from this, and then it's just a matter of putting them into an appropriate results sheet, as you will find in your lecture notes.